So we're looking at the MAT question from 2019, question 2. Have a quick look through, skim reads, and quite pleased to see that P6x in the middle of the question. But it's still not enough. I need to get a feel for this question. So you can see I've written the word specialise because I'm reminding myself that I ought to stick in k equals 1, k equals 2, k equals 3 at least to try and get a feel for this polynomial. Okay, so P2x is going to be what? It's going to be 1 plus x times by 1 plus x squared. If I expand those brackets, what's that going to give me? 1 plus x squared plus x cubed, isn't it? Okay, so still not really see what's going on just yet. So let's try P3 of x, and of course that's going to give me what I had previously, which is the 1 plus x squared plus x cubed times by 1 plus x cubed. And if I do that, I'm going to get, well, I'm going to get the repeat of the first bracket, so I'm timesing through everything by 1, aren't I? So I get all that, and I'm going to get everything multiplied by x cubed. So okay, so I'm going to be increasing the x cubed coefficient and producing some higher powers, and the index numbers are going to be going up. Okay, so, and of course I know what the P6x is because I can look down the page. So you can see that the coefficients aren't going to stay at 1, but go up. And you're going to get 1 at the front, and you're going to get whatever the last power is, x to the n, it's going to be 1x to the n, isn't it? So what can we say? We're supposed to be looking for the degree of n in terms of k. Well, when with P1 the degree was 1. When P of 2 is 3, P of 3 is 6, and blah blah blah, ellipsis, P of 6 is 21. Now that looks suspiciously like the triangle numbers, isn't it? P to the 6, the sixth triangle number is 21 as well, and that sort of makes sense, doesn't it? Because if I multiply brackets like 1 plus x times by 1 plus x squared times by 1 plus x cubed, the final power is going to be simply x to the 1 times by x squared times by x cubed times by x to the 4, etc. And of course indices law just tells me that I can add those together, so I'm going to do 1 plus 2 plus 3 plus 4, which is where the triangle numbers are coming in. So if I want to express the nth degree in terms of k, it's going to be the summation of the triangle numbers, and that's what's that? That's going to be k over 2 times by k plus 1, isn't it? Okay, I'm feeling pretty confident about that, so that's a nice way to start the question. Let's look at this next one. So A max, so A being the coefficients. Right, it does say put x equal to 1, so that's, thank you, that's really good that they tell us what to do. So pk of 1, now let's write down both expressions because they're telling us that pk of x is equal to 2 different things. So I'm going to get 2 times by 2 times by 2, okay, so I'm going to get 2 multiplying by itself k times, so that's going to be 2 to the power of k, which is reassuring because that's, you can see a 2 to the k in the inequality we've got to prove. But of course we're also told, aren't we, that 2 to the k is going to be equal to a subscript 0, a1, a2, a3, a4, all the way up to an. So we've been given 2 equivalent expressions, so I could write down A max has to be greater or equal to A0 plus A1 plus A2 plus AN all over n plus 1. But I don't really want a fraction, so I might multiply both sides by n plus 1. Also, just looking at that P6 down the page, does tell us, just point out what happens is I'm just interested in the maximum value of that. If you look at the coefficients, we're pretty much guaranteed that the first and last are going to have to be 1, aren't they? A(n) x to the n, or a(n) is going to be 1, isn't it? And a(0) is going to be 1. But the maximum value is sort of like symmetrical kind of pattern there, and it looks like the a max will be halfway through. So the maximum term couldn't be repeated. It's just there's going to be, there might be a few of them, but there will not be all of them. So I think the way to proceed here is if I write a max times by n plus 1. That's assuming that every single coefficient is the maximum, is the biggest one, so they're all the same. Times by the number of terms. We've got n plus 1 terms, haven't we? That has to be a greater number than just simply adding up all the coefficients. So yeah, that makes sense. And why should it be greater or equal to? Because when k equals 1 or k equals 2, the coefficients are all maximum ones. It's 1, 1 and 1, 1, 1, isn't it? So that's why we have to have the equal sign. Well, I suppose it's worth pointing out, isn't it, that that apart from k equals 1 and k equals 2, the value of k, the coefficient is always going to be greater than the first and the last. Yeah, so that means that for the majority of cases, the a max times by n plus 1 is going to be greater than all the coefficients added up. Okay, so I think I've perhaps I might just point that out actually, that a max times by n plus 1 for the majority of cases is greater than a0 plus a1 plus a max plus an. I suppose it's not a big deal. But other than that, I think I've got everything that I want to mention there. So it's on to part 3. Fix I greater or equal to 0. Explain why the value of ai becomes constant as k increases. I'm not really sure I understand what that means. So if I fix the value of one of the powers, explain why the value of that coefficient becomes constant as k increases. So as I'm getting bigger and bigger, the coefficients are becoming fixed. Well, that's certainly true, isn't it, for the first 2 or 3 terms. We're certainly going to have always 1 at the beginning, and we're always going to have only an x and only an x squared. You can see from that P6x that that's the case. So I think I need to specialize again. I need to multiply a few out just to get clear in my head what's being asked here. If I multiplied by 1 plus x cubed, I'm getting all the same coefficients when I multiply through by 1, and I multiply through the okay. So the x cubed wouldn't affect anything apart from So if I fix a value of k at I, and I multiply by 1 plus x to the power of I, it's not going to affect any coefficient before it except for the one on the x to the I. So if I is greater, if k is greater or equal to, if x to the power of I is multiplying the the terms with lower indices, it's not going to affect the coefficients except for on the x to the I or more. I need to try and write that clearly. I think I've got it in my head, but can I express it on paper? Let's see. So do you see I'm multiplying by x to the 3, and the 1, when it multiplies through, is not. So if I equaled 3 now, it's not going to affect the lower coefficients, but it will affect this one. So how am I going to write that down? So if I is fixed, let's say if I is fixed, it can only affect the powers lower, like equal or greater than itself, and it can't affect the indices on powers lower than itself. Yeah, and I think that answers what I've been. Well, I think that certainly explains why the value of AI eventually becomes a constant as k increases. Right, part 4. So we've used this P6x, which is super useful, and on the basis of this, the calculation guesses that AI equals AN minus I. I should try and understand that. So if I equals 0, they're saying that A0 equals AN. So the first coefficient equals the last coefficient, the second coefficient equals the second to last coefficient. That certainly looks true on the P6 of x, isn't it? Now they told us to use a substitution, so I'm going to do as I'm told. Don't know quite why I'm doing this at the moment, but let's just see. Let's just go with it. They wouldn't suggest it if it wasn't useful. And of course, I mustn't forget that to make that same substitution into the second part of part 1's the original definition they give us. So that's equal to what? AO plus A1 x to the minus 1. Yeah, that's it. Plus blah blah blah, all the way up to AN x to the minus n. Good. So what do I do with that? Right, well, I don't want any of those on the far right. I don't want any of those negative powers. So if I multiply both sides by x to the n, I'm gonna have this. I'm gonna have the pattern backwards. X. If I can times this by x to the n, I'm gonna get this px. Okay, this is interesting actually. I'm gonna get AO x to the n plus a. Oops. I'm going to get AO x to the n plus A1 x to the n minus 1. Yeah, that's it. Let's keep going. A2 x n to the minus 2 ellipsis dot dot dot, and then A n and AN. That's it. Okay, now that looks interesting, because if I was to write that backwards, then I'm going to get this almost the same pattern, but just the coefficients. Yeah, I think that's it. I think that's it. Okay, so here we go. Let's compare it to what I've already got. So pk of x by itself. Well, sorry, I should have written x there, not 6. Sorry. So what am I doing? I'm comparing. Yeah, I'm just looking at that thing. The first coefficient is the same as the last. The second is the same as the second to last. How do I explain what I've... how about if I write this pattern backwards? So I have AN plus AN minus 1 to the x. all the way up to a0 x to the n, and I compare it then. Yeah, I think that's it. So the student's conjecturing this. He's saying that the student's conjecturing that ai equals a to the n minus I. What I've done, I've specialised for that just to see what he means. What the student means is that, for example, if there's 21 terms, then a0 is equal to a21 minus 0, and the 0th term and the 21st term are indeed the same coefficient. So interesting. What I'm going to do is I'm going to write this second line backwards. Okay. Okay. That's what I mean by that is I'm writing what we're given at the top of the in question part 1. We're given this expansion, aren't we? But I'm writing it back to front. So an minus 2 x to the n minus 2 ellipsis down to well, a1 x1 plus a0. Okay, and that's it. And now if I write underneath that what I've just discovered in the second line, that xn pk of x to the minus 1 equals ao x to the n. Yeah, then you can see that AO is the same as AN, and A1 is the same as yeah. I meant to write it the other way around. But you can compare the second and third lines and see that AO is the same as AN, A1 is the same as AN minus 1, and that's what I wanted to show. So I hope that's enough to yeah. Okay, I'm going to move on to part 5 now. I'm not quite convinced I've picked up all the marks in part 4, but that was the best I could do. Part 5. On the basis of the same calculation, the student guesses that all the whole numbers in the range 1, 2, blah blah blah, up to the maximum value coefficient appear amongst the coefficients A1. Okay, right, so we got from A to, so we got n plus 1 terms, and the student reckons that we're going to get all the integers up from 1 to n represented in the expansion. So why could that be true? Could we have all the numbers from 1 to n if we've got... No, what's wrong with that? That seems quite a fair little. Well, let's see what we've been given. We know that A max is greater than. Oh, sorry, A max is lesser than. Yeah, because the highest coefficient comes in the middle. We've got n plus 1 terms, and the maximum value is going to be, that's definitely true, and we can write A max as 2k over n. Yeah, okay. Right. If we multiply by n plus 1 both sides, we're going to get 2k must be less than n plus 1 all squared, and we can replace the n with what n is equal to, which we worked out in part 1. N, remember, was equal to k over 2 times by k plus 1. Substitute that in there, and you can see that we've immediately got a problem, because we're saying that the exponential is going to remain smaller than the polynomial expression, and there's no way that's ever going to happen. As k gets large, the value of 2k is going to head off to infinity much more quickly than k over 2 times by k plus, and the triangle numbers are squared. So it doesn't look like the student's conjecture could possibly be true, actually. So we can't have all the coefficients representing all the numbers from 1 to n, simply because the value of 2 to the power of k is going to be getting much bigger, much more quickly than the number of numbers that they have to represent as a summation. So I think that's got that. So the second exponential are incorrect because exponentials grow more quickly than polynomials. So this inequality can't possibly hold. And so I'm going to reject that idea and say that it can't possibly be the case that all the whole numbers in the range 1, 2, 3, 4, 5 up to a max appear amongst the coefficients AO to AN. And that's it. That's the end of question 5. Question 2. I thought that was pretty hot, quite a tough test, that one, and not convinced that part 4 is completely correct. So I want to go and look at the mark scheme now, see if I did.